Hey, we're up to page 4. This is about probability, and I'll try to do 2 pages here. Um, Probability, well, let's go with orange this time. Probability is a branch of mathematics that describes, you run experiments, you have outcomes, you know all possible outcomes, but you don't know what outcome will occur when you run a particular experiment at a given time. So you have a well-defined list of outcomes, but you don't know which will occur prior to running the experiment. So an experiment is just a test that can be repeated under identical circumstances. Flipping a coin, rolling a die, shooting a basketball, those are all experiments. I feel like that's too dark. So let's go with light blue. So as an example, I just gave you here's 2 different experiments. Roll a die, record what you get, go down the gym, shoot 10 free throws, count how many you make. An outcome in an experiment is just one possible result when you run that experiment. When you roll a die, you get a 6, you get a 4, you get a 1, you get a 2. If you go down the gym and shoot 10 shots, you could make none of them, you could make 5 of them, you could make 2 of them, 10 of them, whatever. Sample space is just the collection of all the outcomes. So when you roll a die, you get a 1 through 6. When you shoot foul shots, you could make 0 through 10. And then an event is just a subset of the population. So when you roll a die, an event could be getting an even number. When you go down and shoot foul shots, an event could be making half of those. Okay, so here's another experiment. Experiment could be tossing a coin 3 times. If you just want to collect the number of heads in the sample, that would be 0, 1, 2, or 3. That's all possible outcomes when you toss a coin 3 times. The sample space for the sequence of heads and tails, there's 8 possibilities, so that's another sample space. An event in the sample space of tossing a coin 3 times could be getting all heads. An event could be getting at least 2 heads, and there's the outcome. An event could be getting a tail on the second toss. An event could be a sequence, anywhere where you have a sequence of tail heads. Any event that you want, that's a subset of that event. So we can combine events by taking their union, their intersection, their complement. So now that we know what an event is, we can combine events. And throughout this notation here means contained in. So a union, if you remember E, this is the symbol union F, means that an element X is either an F or it's an E, or it could be in both. So if I was to shade this over here, I'll just shade with this. E or F would mean you're an E, or you're in the intersection, or you're an F. So I wish I could erase because I'm a little bit out there, but you get the idea. So here's E, or in between, or F. E or F, or both. So maybe that's this or means at least one. You're at least an E or F, or you could be in both. At least one. Maybe that's nice to say. Let me see if I can write at least E or F, meaning you're in at least one of them. Okay. Down here is the intersection. So E intersect F. E intersect F. That means you're an E and F, and that's just this little piece where they overlap. So it's the overlap, it's the intersection of the two. E complement is everything that's still in the sample space but not in E. So we would get everybody outside here, everybody just in F and not in E. So everybody over here, everybody out here. So everybody outside, sorry about going outside the sample space, but everybody outside of E is E complement. It's kind of fun to draw this way. Okay, there's E complement. I just gave you a couple examples. Here's an event A, B, and C, and I asked you to find the union, the intersections. So A union B is just the combination of A, B, who's ever an A or B or both. B or C, same deal. A intersect B are the elements in both A and B. B intersects C, you can see right here, there's nothing in both of them, so we get the empty set. Here's another example. Roll a six-sided die. Let A be getting a prime number. What's A complement? So event A, prime is 2, 3, 5. So A complement 1, 4, 6. Last definition here. And is this all one? Yay, I'm going to get through 2 pages finally. Mutual exclusive. Oh no, where did you go? Okay, mutual exclusive just means A and B are empty. A and B we say are mutually exclusive if their intersection is empty. They have no elements in common. So here's a nice picture. Here's A, here's B. They don't share anybody. A nice example I think is professors by rank. You have assistants, instructors, associates. You can't be 2 at once. There's lots of nice rules. We're not going to go through and prove them all. If you take statistics or probability, we discuss them. A complement is A. Here's some distributive laws. De Morgan's law. You can see them all with a Venn diagram, but I'm just highlighting there's some nice properties of events when you start complementing them and intersecting them and joining them in different ways. So I feel like, yeah, I might as well do this one while we're here to example 6. If A is still A, B, C, D, I, G, here's B, here's C. What is A intersect B union C? So I would just take, again, the A intersect B, who's in there, and then union it with C. So I'm going to get all of C, and then the rest is just A intersect B, and A intersect B intersects in B, I, and G. And I didn't even mean this to happen, but we get Big Al. Yay. Venn diagram. A intersect B union C. Let me see. A intersect B, I get right here. And then I'm going to union it with C, so I get all of C. I mean, when you union with something, you get all of that thing. So here means I'm in C or I'm in A intersect B. So there's my picture. Shaded diagram of A intersect B. A lot of people have trouble with A intersect B. Just disregard C. A intersect B is this area here. I'm not saying I'm in C or not in C. All I know is in A intersect B. So ignore C. I don't want to make a statement about if it's in or not in. So that's pretty much the basics of probability and keywords and combining events. And next we'll define probability. Okay, let's turn this off.